In this video, I am going to talk about taking limits as x goes to infinity for a function, and for a particular function, rational functions. So we're interested in the limit as x goes to infinity of some function f of x, or the limit as x goes to negative infinity of this function f of x. And f of x is a particular form. It's a rational function. So it's got a numerator and a denominator where n of x and d of x are polynomials. Okay. Now, the way we're going to do this, you usually learn there are three cases, and we're going to work through our three cases, but I'm going to give you a strategy which works for everything. So I want a strategy that lets me take these limits no matter what, and we'll see the three different cases that one often learns sort of come out of that. So the thing to observe is that if we've got a polynomial, let's look at, say, the numerator, right? So the numerator is some polynomial. I'm just going to write one down. It doesn't matter what it is. So we'll do 4x to the fifth minus 7x cubed plus x minus 2. If we're interested in the limit as x goes to infinity of n of x, well, this function obviously gets very, very big. But if we think about this limit for a second, we think about what happens when we plug very, very large numbers, very large x, into this function. Well, we've got 4, let's say a million. 4 times a million to the power 5 minus 7 times a million cubed plus a million minus 2. If you think about those four numbers for a second, you'll notice that it's actually dominated by this 4x to the fifth. Right? A million to the fifth is a much, much, much bigger number than a million cubed. And if it's not big enough for you, take 10 million or 100 million or a billion and take that to the fifth, and you'll see that that's much, much bigger than x cubed. And what that means is this limit is the same as if we took the limit as x goes to infinity of just the leading term, just that 4x to the fifth. Okay, so we can, if we're taking a limit of a polynomial, we can just worry about what the leading term does, and if the leading term goes to infinity, we know it does. But now we can use that observation when we're taking the limit of this fraction, of this rational function. So I'm just going to work through some cases here to see what happens. So first, and remember, the degree of a polynomial is that first term, that leading term, the term with the highest coefficients, the coefficient. Or sorry, the exponent, the number in the exponent. Okay, so let's say case number 1, degree of the numerator is less than the degree of the denominator. Okay, so let's just do an example, and it will show us how to solve these sorts of problems. So we're going to do the limit as x goes to infinity of, let's choose one. Let's choose a slightly easier one, so I have to keep writing it down. 4x to the fifth plus x minus 2 over, and the degree of the numerator is less than the degree of the denominator, so we've got a fifth up here. So we're going to do a 7, let's make it negative 7x to the 10th plus 1. Okay, so we're going to use that trick that I told you. Right, we're just going to worry about those leading terms. So this is the same as the limit as x goes to infinity, just the leading term in the numerator, 4x to the fifth over negative 7x to the 10th. So that should be a 5. Okay, well, this we can simplify. 4x to the fifth over negative 7x to the 10th, well, that's the limit as x goes to infinity of negative 4/7 x to the negative 5. Well, we know as x gets really, really big, x to the negative 5 gets closer and closer to 0, so this just simplifies to be 0. Okay. So, and again, the normal way of thinking about this, or one way of thinking about this is, or you learn a rule, the rule is if the degree of the numerator is less than the degree of the denominator, the limit is 0. And again, you can think of another way to think about that is the denominator gets big much, much faster than the numerator. So 0. Okay, so let's do another one. The degree of the numerator equals the degree of the denominator. Okay, so let's write down an example. Limit x goes to infinity, 4x to the fifth plus x minus 2, all divided by negative 7x to the fifth plus 1. Again, same strategy. Look at just the leading terms. Limit x goes to infinity, 4x to the fifth over negative 7x to the fifth. Well, that's equal to the limit, we simplify, x goes to infinity, of negative 4/7, which is negative 4/7. And of course, the rule that we learn is that if the degree of the numerator is equal to the degree of the denominator, the limit as x goes to infinity is the ratio of the coefficients. Now for our last case, case number 3, the degree of the numerator is bigger than the degree of the denominator, and we need to think a little more carefully here about this one. So nothing changes, it's just we need to think about our results a little bit. So limit as x goes to infinity, and we'll use the same function, 4x to the fifth plus x minus 2 over negative 7x cubed plus 1. So we can simplify this to just our leading terms. X goes to infinity of 4x to the fifth divided by negative 7x cubed equals the limit as x goes to infinity of negative 4/7 x squared. Well, as x gets really big, x squared gets big even faster. So x squared goes to positive infinity. We've got a negative 4/7 here, so that's going to go to negative infinity. And this is where we need to think a little bit before we take our limit. So if we're going to positive infinity, then this limit is going to be infinite, plus or minus infinity, and we're going to decide between plus and minus infinity by looking at this coefficient, right? This coefficient's negative, we're going to positive infinity, we've got an x squared there, so we go to negative infinity because of that. Now, if we're going to negative infinity, you can see where this gets a little complicated, right? We've got x squared, still sign of the coefficient. If this had turned out to be x cubed and we were going to negative infinity, well, x cubed, when we take x gets really, really big and negative, x cubed still goes to negative infinity, and we'd end up with positive infinity. So we have to think a little more carefully to figure out the sign. It's always going to be plus or minus infinity, but we have to think a little bit in terms of coming up with that sign. So let me do one more example just to demonstrate what I'm talking about here. So the limit as x goes to, let's make it go to negative infinity, 4x to the fifth plus x minus 2 divided by negative 7x squared plus 1. And so that's the same as the limit as x goes to negative infinity of negative 4/7, and now we've got an x cubed. Well, when x gets really big and negative, x cubed becomes even bigger and negative. We have a negative times a negative, so that's going to equal positive infinity. So like I said, we need to be a little bit careful here when we do this last case, when the numerator is bigger than the denominator, to decide what happens. That doesn't come up in the first case because we're taking 1 over a really big number. We're going to head to 0. In the second case, we have the same degree in the numerator and the denominator. It all cancels out, so it doesn't, all that comes in are those coefficients. In this last case, numerator bigger than denominator, we have to worry a little bit about what's going on with our sign to get it right, this can come out to plus or minus infinity, depending on the sign of the coefficients, the degrees of the numerator and the denominator, and whether we're going to infinity or negative infinity.